We now welcome on stage the first competitors of the day, Ma and Luo from the International School of Luxembourg, who will present a study that explains the mechanisms behind Fourier Analysis device experiments to gain further insight. Good luck, Ma and Luo.
Good morning, dear honorable members of the jury. Today, Ziqiao and I will present you an introduction in Fourier analysis and its application in a variety of fields. Allow me to introduce you the main character of the show, the equation of Fourier transform.
They're usually taught to engineering and mathematics undergraduate students in their third or fourth year. It is the cornerstone of modern signal processing due to its ability to transform between its frequency domain and the time domain.
Furthermore, Fourier analysis can be used and was initially used to solve partial differential equation, which models a range of physical change involving functions of several variables, such as heat flows and sound propagation.
However, we're all born to know how to do this complicated calculation. In fact, our ears and brain perform this intricate task continuously and subconsciously. However, this mathematical marvel and one of the most elegant equations in history was not discovered until the late 18th century by the French mathematician Joseph Fourier.
So the profound interrelationship between time and frequency domain was succinctly summarized by the two equations on the previous slide. So here, this diagram illustrates the core concept behind Fourier transform. As we can see here, we've got a signal, and according to Fourier theorem, it is a composite of those three sinusoidal waves. Therefore, if we apply Fourier transform to this signal, we are expected to see three peaks at its frequency spectrum, which corresponds to the frequency of those sinusoidal waves.
Okay, so here's the first application we introduced. So as we explained earlier, Fourier transform essentially specializes in the analysis of spatial frequencies, such as here seismic waves, where it is usually applied to find out the losses due to an earthquake. And in this diagram, here are the four most common ways where seismic wave propagations can damage a land feeling. And by keeping a record of the previous seismographs, such as this diagram, it's an example of a seismograph, well, it can actually help us to build more earthquake-proof buildings. And how do we do this? The idea is to analyze the common frequency spectrum, such as this diagram, the red portion, and so that the natural vibration frequency of a building does not resonate with the earthquake's frequency, therefore having a greater chance to withstand the effects due to an earthquake.
So the second application explored by the paper is image compression. In the digital era, image is stored as a giant matrix full of ones and zeros in our computer. Therefore, when we're compressing images, we're simply dealing with the numbers and modifying the numbers within those matrices. So the most common way of compressing image is the Jpeg algorithm, which divides, for example, this big image into 8 by 8 pixel blocks. And the intensity of each pixel corresponds to the position of the particle on the wave. Therefore, we can apply Fourier transform to this image and obtain its frequency spectrum. Then what we can do is to eliminate all the extremities on the frequency spectrum, which correspond to high frequencies. And because human eyes cannot appreciate the minute, sharp difference in colors, by eliminating the extremities hence higher frequency denoting sharper difference, we're able to reduce the size of the image significantly without losing much of the quality. However, it is worth noting that we can achieve further image compression by removing basically more frequency in the frequency spectrum. However, we will definitely lose more quality.
Yep, and here's our third application using Fourier transform. It is the application in the computed tomography. Essentially, information is obtained through individual slices, through the emission of X-rays from different projection angles. And thus we can analyze the frequency spectrum through different angles to reconstruct our intended object. So it sounds pretty abstract, I suppose. So here's my analogy. Essentially, the block is the intended object we're trying to reconstruct. We first project from the angle of 0 degrees, and then we get to a slice of information, and then we project another time. So from the bottom at 90 degrees, we get a different set of information. And then we can use these two slices to work backwards using Fourier transform to find the original block using those two projections. However, as we know that there can be multiple possibilities we can reconstruct in this case, because two projection angles is not enough to recreate a precise enough of object. So if we were actually scanning a tumor in the body, such as it's represented by the white dot in this image, so the direct application of Fourier transform, as I kind of explained in the previous slide, it actually doesn't present the whole picture due to its limited number of projection angles. So the more projection angles we take, well, there's supposed to be a contrast.
Apologies,
yeah. So with less projection angles, the shape of the tumor is not as precise as we would have liked it to be. And with more projections, we can grasp a clearer image and maybe reconstruct a clearer tumor in the body.
So the last application investigated by the paper is noise canceling. Sorry. The key idea behind noise canceling is the superposition of two sound waves with a phase difference of pi. And we have devised an experiment to validate our theory of noise canceling, which can be applied in numerous noise canceling headphones. So we connected a signal generator with a single speaker to produce a pure sound wave first. This is our results. We have recorded using our phone application its frequency spectrum and its time domain, so we can see its waveform as well. In the second part of the experiment, we want to investigate the destructive interference of two sound waves. Therefore, we linked another speaker to the generator. However, we reversed the input-output to generate two sound waves with a phase difference of pi. And then we measure the distance between the two speakers and place a ruler along the line of symmetry, because that is where we can, well, most probably find the superpositions of destructive interference, because the energy of the waves from the two speakers are the same along the symmetry line.
And in fact, we have managed to find a few positions of destructive interference along the axis of symmetry, as shown in this whole table. And the amplitude of the noises is visibly reduced from the figure on the bottom left. As we can see, the amplitude is reduced, and everything is basically below 0.005, as against the figure on the right, where the amplitude is kind of imbalanced. Well, and also another feature we can notice is that on the figure on the right, there's no visible peaks and troughs. And also the intensities of the frequency all fell below 0.001 on the upper left figure. Therefore, our theoretical destructive interference between the two waves is actually proven. But I don't think it's very possible to show a complete absolute noise cancellation with our experimental setup. Reasoning being the inaccuracies within the devices as well as the background noises.
Yeah, sorry, just a quick side note. The one application of the noise canceling is, of course, the noise canceling headphone. So what happens is they have a microphone which I guess, gets the outside noises, and they have a speaker within the headphone which produces the sound wave of a phase difference of pi. And as I have demonstrated, this could possibly achieve destructive interference, therefore noise canceling. Thank you for your time. We entertain any and all questions you may have.